Hey guys, so in this video I'm going to be going through the 2018 mechanics paper. So yeah, let's get right through it. Alright, so question one. The Electron rocket developed by the New Zealand company Rocket Lab has begun commercial launch of satellites from the Mahia Peninsula and Hawke's Bay. Can carry a satellite mass of 150 kgs to a stable orbit of 5 times 10 to the 5 meters above the surface of the Earth. Show that the force due to gravity on the satellite in this orbit is 1270 newtons. Okay, so we know that to calculate, hold on, let me just get this like, yeah, there we go. All right, so Fg equals G M on R squared, which is just going to be the gravitational constant um, times the mass of the Earth, which is 5.97, I'm pretty sure. Yeah. 5.97 times 10 to the 24 times the mass of the satellite, which is 150 kgs, all divided by. Now, keep in mind that we have to take the actual distance from the center of the Earth, so it's actually going to be um, the radius of the Earth. Oh god, radius of the Earth plus, right, whatever, like, let's just assume that's a circle, okay, plus this height h, right, above the surface of the Earth. So in this case, h equals 5 times 10 to the 5, and the radius of the Earth is this. So let's go ahead. So we're just going to do 6.37 times 10 to the power of 6 plus 5 times 10 to the 5, and all of that squared. And putting all of this in my calculator, that gives me like 6.67. I get like 1265.55 newtons, which is 1,270 newtons to three significant figures. Um, so that's that one. The rocket, the satellite, and any space debris at the same altitude in stable circular orbits will all travel at the same speed. Show that this is always true by deriving the formula for orbital velocity and use this to determine the orbital velocity of the satellite. Okay, so for the first condition for an orbit is that your centripetal force must be equal to your gravity force, right? And subbing in their respective equations, we get mv squared on r is equal to gmm on r squared, and we can just cancel these r's and m's to get v squared equals gm on r. And so your orbital velocity v orbit, let's just say, you know, vo, is equal to the square root of gm on r. So that's that one there. Okay, let's start our working fresh over here. So v will just be the square root of like 6.67 times 10 minus 11 into 5.97 times 10 to the 24, and all of that divided by, once again, your radius plus your height. So I think that's 5 times 10 to the 5 plus 6.37 times 10 to the something, I forgot. 10 to the 6, okay. And putting all of this in my calculator, and I get like 7613.28 meters per second, which comes out to 7610 meters per second to 3 significant figures. To the, and use this to determine. Yeah, so we've done that part. Okay. A 20 kg piece of debris, space debris, showing the same altitude and speed, okay, as a satellite, but in a direction that is, okay. Okay, cool. So let's just put this in a more simplified diagram, but we've got like this 20 kg piece of debris, right? All right. And this 150 kg satellite, right? Calculate the center of calculate the distance between the center of mass of the system and the satellite. Okay, so what we want to do is take this as our starting point and find how far is this xcom, right? So our equation for xcom is m1x1 plus m2x2 divided by the total mass, which is m1 plus m2. And in this case, our m1 is going to be 20 kgs, 20 kgs, and that is 1.08 times 10 to the 4 meters away. 1.08 times 10 to the 4 will be this distance here, right? So 1.08 times 10 to the 4 plus, now the mass of our this next object is 150 kgs, but we are measuring it from the origin, this point here, so that's just going to be 0. And the total mass is just going to be 150 plus 20, which is 170 kgs. And putting this all in my calculator, 20 times, I get 1270.59 meters, which is just 1.27 kilometers to, wait, I think I'll just leave my answer in meters. So you'll just get 1,270 meters to 3 significant figures. Describe the motion of the center of mass of the system as the continue to move along their path. Okay, so we know that the center of the motion of the center of mass, the motion includes the that would include speed and direction, right? The speed and direction of the center of mass will remain constant. It will remain constant. It would remain constant, like assuming like no external forces, or unless acted. Yeah, okay. It will remain constant unless acted upon by an external force. So that's that one there. Cool. All right. The debris collides and becomes embedded in the satellite. Calculate the speed and direction relative to the initial direction of the satellite. Calculate the speed and direction. Okay. Okay, so that means we have to... Okay, our velocity we calculated was like... Okay, so let's break this into our first part, right? So let's find P initial, right? So P initial will just be M1V1 plus M2V2, right? Which is just going to be 20 into like 7613, I think, was it? Plus 150 into the same value, so 7613, which is just going to be 7613 times 170, which is it's a massive number. I'm just gonna put that into like scientific. So that would just be 1.29 times 10 to the power of 1, 2, 3, 4, 5, 6 kg meters per second. So sweet, we've worked out our initial momentum. So if we represent this as a vector, then we know that like our initial momentum was in no, we had like two. So we had this momentum of the debris, which is 20 bracket 7613, and then we also had the momentum of the satellite, right? And going this direction. I'll just put it the other way around. Hold on. Yeah, I think like that would be better. So we had our momentum in the x direction, which is 20 bracket 7613, and then we also have this momentum of the satellite, which is pretty sure that's yeah. Um, and that was going at 150 bracket 7613, right? So because we know that the like assuming no external forces, right? Momentum is a physical quantity that's conserved. So the only way to close this vector, because closed vector sum to zero, so would be to draw this, and that's orthogonal. So this means that our final momentum would be like this, right? So now to work out our final momentum, PF will just be using the Pythagorean theorem, the square root of uh, the momentum of debris and momentum of satellite. So PD squared plus PS squared, which is going to be the square root of 7613 into 170, which is just going to be oh sorry, I didn't even square it. Hold on. I just realized. Wait, oh no, it's frozen. Great. Okay. Hello. Alright, in the meantime, I'm gonna put the thing in my calculator. So, oh god. Okay. So we're gonna get like the square root and I get like the square root of all of this. Hold on, I'll just put it into write it like that. So 20 times 7613 squared plus 150 times 7613 squared, and all of that comes out to, it's a massive number. Yeah, like 1.152 times 10 to the power of 1, 2, 3, 4, 5, 6 kg meters per second. So our final momentum is this. So we know that I'll just continue this like up here, but our final momentum must be equal to our total mass multiplied by our final velocity. So our final velocity would just be the final momentum divided by the total mass, which is just this number here divided by 170. So 1.152 times 10 to the 6 on 170, and I get like I get 6776 6776.8 meters per second, which is 6780 meters per second. Three significant figures. Cool. So we found the final velocity, but now we need to like find the direction. Okay. Okay, so for the final direction one, right? So the initial direction of the satellite was like this, right? And then it's sort of and then there was this momentum coming in from this direction, right? Which would have caused this blue vector here to rotate a bit in this direction, right? So like so it would maybe, let's just say, go off at some angle theta, right, in this new red direction here. So what we can this is basically the exact same vector diagram. So you're just going to have your momentum of the satellite in this case, which yeah PS, okay, PS, and then you're literally just gonna have your momentum in the x direction, which was the debris, and then you just have your final momentum, right? And so this angle theta is relative to the initial direction um, of the final momentum. So we know that PD is just, debris was 20 by 20 times 7613, and I'm just going to use the tan ratio for this one. So, and PS is just like 150 into 7613. And so theta is just going to be the inverse tan of PD on PS, which is basically the inverse tan of 20 on 150, which in degrees, let me just make sure my calculator's in degrees. So the inverse tan of 20 on 150 gives me like 7.59, 7.59 degrees to three significant figures. So yeah, so basically this vector caused the final total momentum to be shifted by 7.59 degrees. So yeah, okay. All right, so that's that one done. Yeah, we did everything right. Yeah, cool. Question 2. Whether satellites can be launched into orbits that circle around the north and south poles, and this enables the satellite's camera to view the whole of the Earth's surface as the Earth spins underneath, is 101 minutes. Okay, okay. So we know that omega equals 2 pi on the period, and in this case 101 times 60 is going to be our period in seconds, so that's just going to be 2 pi divided by 101 times 60, which is 1.0368 times 10 to the minus 3 radians per second, which is 1.04 times 10 to the minus 3 rads per second, to three significant figures. I'll change the color. Blue's better. This angular velocity is achieved by firing two 5-Newton thrusters attached on opposite sides of the satellite's 1.6 meter diameter. Okay, so imagine like if I had like a satellite, right? And okay, that's not what it looks like, but okay, it's probably okay. Just let's just say it's like a rectangle. Then I've got like a thruster, one thruster on opposite sides, right? So I would have like some thrust coming out of here, which would create a force in this direction and a rotational torque, right? But this, so basically using one thruster, using one thruster, you will get translational as well as translational and rotational motion. And this also means that since you get translational motion, that that the motion of the center of mass would be changed. This means the motion of the center of mass will be changed because it's an external force, right? Will be changed. And so if we had another of this thruster, right, in this direction, then we have a force in this direction, but a torque in this direction. And check that out. These two forces, they're opposite each other, so they cancel out in magnitude. So having two thrusters causes the net force to be zero, right? But the rotational torques add up, right? They add up. So, I mean, yeah, folks, add up, resulting only in rotational motion. Cool. Okay. Sure. Okay, so I'm gonna just highlight these numbers then real quick. The thrusters are fired for 6.48 times 10 to the minus 3 to set the satellite rotating at the required angular velocity. Am I given any other numbers? Yes. This one. And that one. Okay. Let's see. Alright, what do I actually need for this? Okay. So, alright. So if I think we could use this equation here. T equals I alpha. It's fired for this. So alpha is just going to be the change in omega over the change in time, and our torque. Oh, we can calculate the torque, right? So we have the satellite's 1.6 meter diameter, so our torque is just right. So it's gonna be like, let's just say that's like, oh, okay, so it's probably a circle. All right, so that's 1.6 meters. So from the center, right? So you got one torque acting here. So you got 5 newtons in this direction acting at 0.8 meters. So torque is just going to be 5 newtons times 0.8, sorry, not 0.11. Oh yeah, no. So, and 0. Times 0.8, and we're going to have two of those because you got one 5 Newton acting here and another 5 Newton acting there. So two lots of that, and putting this in my calculator, 10, that's just 8. That's just 8 newtons per meter. Okay, so cool, we know that. Now, okay, let's say alpha, right? Alpha is d omega by dt, right? So that's just, our change in omega is going to be, let's just say it's from, I'm going to assume it starts from 0. So it's going to go from 0 to 1.04 times 10 to the minus 3. Oops. So that's going to be 1.04 times 10 to the minus 3 divided by 6.48 times 10 to the minus 3 also. And putting this in my calculator, it's just 1.04 divided by 6.48. Oh my god. And I get like 0.16. Yeah, 0.16 radian per second. Okay, cool. So T equals I alpha and I equals T on alpha, which is 8 on 0.16, which is 50 kg. I'll just put that in my calculator. But yeah, 49.85 is what I get. 49.85 kg per square meter, which is 50 kg per meter square. So yeah, okay, that's done. Nice. Okay, let's have a look at this one here. Instead of using two thrusters to adjust the angular velocity of the satellite, it is often preferable to use a reaction wheel system. Okay, and when the wheel turns in one direction, the satellite will spin in the other. Bill is solid and has a rotational inertia given by half mr squared, the radius. Okay, I'm just gonna write down my numbers because there's quite a bit here. So the mass of the wheel is 5 kgs, and the radius of the wheel is 0.2 meters. And let's just calculate the inertia of the wheel. So the inertia of the wheel is just going to be IW equals mr squared on 2, which is just 5 times 1 on 10, that's just a fifth squared, divided by 2, which is just going to be 0.1 kg meter square. Okay, I don't trust myself. I'm going to put that in my calculator just to make sure I got that right. Yeah, okay, I got that right. Okay, good. And the inertia of the wheel is 0.1 kg meter squared. Okay. Anything else? Oh, yeah. And the inertia of the rotational inertia of the satellite is 50. Okay, and inertia of the satellite equals 50 kg ms kg meter squared. Kg. Okay, so calculate the angular. So to keep the let's work out, because it has to keep the camera pointed at the Earth, right? So this means that the angular velocity of the satellite, the angular momentum of the satellite will just be I omega, which is just going to be 50 into, let's do that across, 50 into 1, no, hold on, 1.04 times 10 to the minus 3. 1.04 times 10 to the minus 3, which is 50, 0.05 to kg per meter square, kg meter per second, meter squared per second, yeah. Okay. So this, for the, okay, so basically we know that assuming no external forces or torques, L, or angular momentum, must be conserved, right? Which means that the angular momentum of the satellite must be equal to the angular momentum of the wheel. So the inertia of the satellite times omega of the satellite must be equal to the inertia of the wheel times the omega of the wheel. And we are trying to find the omega w, omega the wheel. So omega w equals just is times ws on iw. And do we know is? Yes. Do we know ws? Yes, we do. We do know omega s. That was this number up here, 1.04 times 10 minus 3. Omega s equals 1.04 times 10 minus 3. And inertia of the wheel, we calculated 0.1, which is okay. So this is just going to be inertia of the satellite. It's just going to be 50. And the angular velocity of the satellite is 1.04 times 10 minus 3, and all of that divided by the inertia of the wheel, which is 0.1. Putting all of this in my calculator, 50 into I get 0.5184 radians per second, which is 0.52518, 0.52 radians per second. So yeah, that's that one. Yeah, stated my assumptions and I worked out the angular velocity of the wheel. Alright, hope it's right. When astronauts return to Earth, a spring under their seats reduces the force during the landing. The astronauts' kinetic energy is converted to spring potential energy as the spring is compressed. If friction is negligible, then simple harmonics. Okay, so for simple harmonic motion, we know that your acceleration must be proportional to your displacement, as per a equals negative omega square y, and your restoring force must act to equilibrium as per the negative. Okay, let's see. Any numbers? No. Alright, so during a landing, an astronaut and a seat had a combined mass of 80 kgs and were set into a simple harmonic motion with an amplitude of this and a period of this. Determine the spring constant. Okay, T equals 2 pi times the square root of m on k is, I think it's that. Let's see. T equals, yes, T equals 2 pi root m on k. So do I know my T? Yes. Do I know my M? Yes. So let's rearrange for K. So rearranging this for K, so you get M on K is equal to T squared on 4 pi squared. And so K is equal to 4 pi squared times the mass divided by your period squared, which means that K is just going to be 4 pi squared into 80 on 0.94 squared, which gives me 4 pi squared into 80 on 0.94 squared, which is like 3574 Newton per meter, which is 3570 newtons per meter to three significant figures. So EP equals half kx squared, and it displaces by that much, so a half into 3574 into 0.15 squared, and 1/2 into that into 0.15 squared, and I get like 40.2 joules, the three significant figures. Okay, reference circles, great. Isn't that gonna be fun? Alright, let's have a look. Determine the velocity of the astronaut when he is 0.1 meter above the equilibrium. So this is the equilibrium, so I'm just gonna assume that, let's just say this vector is here and he started along this line here. So this length here is going to be 0.1, this is going to be 0.15, and the angular displacement of the vector or theta will be this. So we know that, let's first of all work out the angular velocity. Omega is equal to 2 pi on the period, which is 2 pi on 0.94, which gives me 2 shift pi on 0.94, and that gives me 6.68 radians per second. And next thing, okay, because we're doing this from amplitude, that means our position will be starting from cosine, so that means our velocity would be like negative v equals negative a omega. Yeah. Okay, so wait a second, hold on. Above the, okay, so if we start from equilibrium, that will be sine, and so that would, yeah, that would become cosine. Okay, so we would just use v equals a omega cos omega t, which is theta, right? Yeah, that makes a bit more sense. I don't know what I was yapping about before, but so do I know my a? Yes. Do I know my omega? Yes. Do I know my theta? No. Let's find theta. So theta is going to be the arcsine of 0.1 on 0.15, which is, okay, in radians. Put that in radians. Arcsine of 0.1 on 0.15. I get 0.7297 radians. And so starting from equilibrium, above equilibrium, um, so V equals A omega cos of theta, which is just going to be 0.15 into 2 pi on 0.94 times the cosine of the inverse sine of 0.1 on 0.15. This is just in exact form, I'm trying to give it as exact as I can. So 0.15 and then 2 shift pi on 0.94 times the cosine of all of that, and I get 0.747 meters per second, which is 0.750 meters per second. Yep. Okay. Alright. Yeah, sweet. We got that one then. Wait, hold on. I just want to try one thing on my calculator. Let me just see if that actually works. Okay. There's another approach I think I can take to this question here and get the exact same answer. But I'll leave that for like, I'll probably leave that for like another video, because that's pretty cool, I reckon. Yeah, so that's kind of sick. Yeah, okay. I'll leave that for another video. That's actually pretty cool. Okay. The motion of the astronaut is quickly brought to rest by a damping system on the spring. So damped harmonic motion can be modeled in the lab with a mass, a spring, and a beaker of water. description of what is meant by damping, how a damping force in the lab, and how it will impact the motion, and a sketch of a graph. Oh no. You all know what happened in the last video, man. Oh god. Alright. Okay. Let's see. So basically we know that damping is basically this system is going to be oscillating up and down and up and down and up and down and up and down. It's just going to like lose energy, right? So damping is the loss of energy of an oscillating system, right? Because of an oscillating system to the surroundings. Right? And damping of the in other words, it's basically the restoring force, right? Because it's always trying to bring this oscillating thing back to equilibrium, right? To the equilibrium point. So basically the direction of the damping force, let's just say, you know, the D dot F is always to equilibrium or opposite to the direction of motion, in other words, right? And okay, right, so I guess we kind of got that bit nailed. So let's move on to this one. Basically, oh god, wait, hold on, my cable's tangled. All right, there we go, that's better. Right, all right, let's go back to it. It will so basically this let's just call it our back to our restoring force will absorb, no, it wouldn't, basically this restoring force will oppose the motion, right? And this will result in the energy of the system to not be conserved and lost to the fluid in the surroundings. I'll just say surroundings. And so surroundings, oh god, resulting in a smaller amplitude over time. Yeah. Oh god, alright. Okay, so I think it would like usually like the thing would like fall in like some sort of this kind of like, this is just like a guide for me, but it would, let's just say, maximum downward displacement. So that means this, what was the amplitude again? Do we know? Do we get any numbers? Nah, it's in a lab. So I'm just gonna say this is A plus, and this is gonna be your least lowest displacement. So it would sort of just start here and then come down and then go up and then hold on. How many cycles did they say? Did they? Hold on. Alright, then I guess I'll just do as many as I'd like. Let's get okay. Well then, yeah. Okay, well, I guess I'll just do as many as I'd like that I can actually reasonably fit in here, which should probably be that many. So actually, this is not that bad. This is not that bad. But yeah, no, that's it for this video, I guess. Well, let me actually see in the assessment schedule how many did they actually do. Um, they did 1, 2, 3, 4. Is it? Oh, okay, then that's all right. Sweet, that's all good then. Yeah, so yeah, it is decreasing. Yeah, sweet. Yeah, so that's the 2018 mechanics paper done. Thanks for watching.